from Paris 7, and starting in the fall, they call them Mile Superior. Zoé is a French citizen, which you can tell from her name, Chatzidakis. And she spent a sojourn in the United States with a Yale PhD from the mid-'80s, and she's been one of my friends and sometime collaborator since that era. She went to Princeton after she got a PhD, and then to CNRS. She is now someone who plays a leading role in the model theory, especially of algebraic structures applications. And recently, she received the LeConte Prize from, I think, the French Academy. It's my pleasure to introduce Zoé. Her title is Model Theory of Difference Fields and Application to Algebraic Dynamics, and I think she's going to make an unusual request of us.
Thank you, Carol. I can't pace. Really pace. So I'm going to please speak into the microphone. Just hold it. I'm going to speak about some application of the model theory of difference fields to algebraic dynamics. So I guess I first need some definitions. A difference field is a field with a distinguished endomorphism, which automatically will be injected. It becomes naturally a structure in the language of rings augmented by a binary function symbol for the endomorphism, which I call sigma. Sometimes the endomorphism is surjective, in which case the field is called an inversive difference field. And every difference field has a unique, up to isomorphism, inversive difference closure. Okay, so that's one definition. Second definition. What I call an algebraic dynamics is given by an algebraic variety V, which I suppose always to be absolutely reducible, quasi-projective. And together with the rational map phi, which goes from V to V, and again, I'll make assumptions that my map phi is dominant. I'll say that the system V phi is defined over K in case all the data is defined over K, but of course, like most model theorists and in my varieties, I will view them as varieties over any extension. Okay, so what is the connection between those two? Okay, first of all, let me give an example of a difference field. So the typical example, and actually it's the example from which you get the name of difference variety, or difference field, is the field of rational functions over C, where sigma is the identity on C and sends t to t plus 1. So in other words, if you have a rational function f of t, sigma of f of t is just going to be f of t plus 1. So this generalizes to algebraic dynamics. I mean, any algebraic dynamic will give rise to a difference field as follows. You take the function field of the variety V. So, as I said, my varieties are projective, quasi-projective. So, if you want, let's say that, let's describe it in the affine case, you are just talking about a zero set of polynomial equations. And because I want them to be absolutely reducible, let's say my field K is algebraically closed, I want that the ideal of polynomials vanishing on points is prime. So you start with your polynomial ring, you quotient it by this ideal I, you get the affine ring of the variety, then you take the field of fractions of this, and you get the function field of the variety. Now the elements of this function field, they are going to be quotients of functions which are defined everywhere on the variety. So necessarily they are not going to be defined everywhere, but they still give you an idea of, they give you a concept of a function which is going to be defined on the k points of V and which takes their values in k. So the endomorphism of the variety then the endomorphism phi has a natural action on k of V simply by composition. You take you take your rational function f, you view it as a function from B of k to k, and you can pre-compose it with phi. It gives you another function. Okay? Right. So this difference field I denote by, I denote the endomorphism by phi star. You notice that usually so first of all, phi star is going to be the identity on the ground field k. That's by definition. And usually it's not going to be it's not going to be onto simply because phi is probably is not injective. All right. Okay. Right. So there is a invariant which is called the degree, and which equals the degree of k of V over the image by a phi star of k. Right. So that's the connection between the two objects. So, right. So I'm going to ask you to close your eyes while I go to page 18. Okay, so the result I want to talk about is the following result. It has to do with algebraic dynamics. So one of the things, I was mentioning that you had an algebraic dynamic defined over K, but you could view it as an algebraic dynamics defined over a larger field. Now there is a question of whether sometimes so you have this variety defined over a large field, and you would like to know whether it's isomorphic to something which is defined over a smaller field. Okay, so there is a situation where you almost get that result. So I'm going to state a simple case of that. So we start with a field K. We then take a function field over K, so K of T. Let's call it L if you prefer. And we have two algebraic dynamics, V phi, W psi. V phi is defined over the large field, over K of T. W psi is defined over the small field K. Nevertheless, you have a dominant map from W psi onto V phi. Meaning, so you have a dominant map of the variety such that the obvious diagram commutes, in other words, phi circle G is equal to G circle psi. Now, you would like to be able to deduce from this that actually the two varieties, the two algebraic dynamics are isomorphic. It does happen in certain cases, but first of all I should mention that because the techniques used are going to be difference fields, in other words, I'm going to work with the function field of the variety V and the function field of the variety W, the only results I can hope to obtain are going to be birational. Okay? So I'm not going to be able to get, in any case, full isomorphism, but just maybe birational isomorphism. And it's not always in all cases. We have some examples where you do not get isomorphism. Okay. However, you get a fairly strong conclusion. You get that this V phi, while itself is not isomorphic to something defined over the small field K, but it's going to have a quotient, V0 phi 0, which will be defined over K. And moreover, the degree of phi 0 and the degree of phi will be the same. In other words, if you were starting with something which had degree greater than 1, the V0 phi 0 is not going to be just a point, it's going to be something bigger. something of positive dimension. And one gets some additional condition, which is that the generic fiber of this map is what I call internal to fixed sigma. I'll explain this meaning a bit later. Grosso modo, it means, so you see, if you look at a generic point of V0 and you look at its inverse image under the map H, you are going to get what's called a difference variety. In other words, things which satisfy certain difference equations. And actually, there will be a map from that into points which satisfy into a Cartesian power of the field of points satisfying sigma less results. So that's what I call internal. Okay. Then comes a sort of technical assumption, which I'll explain later, and which tells you that in that case you can actually get, well, in characteristic 0 you're going to get this H to be birational. In characteristic P you might have to compose it, to pre-compose it by some power of the Frobenius, some negative power of the Frobenius, positive power or something. Okay? So you get something which is still quite good. Okay, so let me say these hypotheses might be a bit strange. I mean, they seem to be a bit contrived. Actually, what they do occur in life. And let me state what we wanted to prove, really. And this comes from the following. So we are still in this situation of this algebraic dynamics B-phi defined over K of T or over any function field. And we are assuming that it's polarized, so there are lots of technical assumptions, but let me for the logicians, give a simple case of this. So we have phi defined over K of T, and we assume that it's embedded inside projective space, Pn, okay? Now, we assume that the degree of phi is going to be bigger than 1. And we are assuming that for some integer n, if you look, so points of projective space, they are over K of T, they are going to be represented by n+1 tuples of polynomials of a certain degree. Polynomials over K. Polynomials in Okay. So the degree, the minimum, so of course, because you're in projective space, you need to take those polynomials to be relatively prime, right, as well. And then the highest degree of one of these polynomials is what's called the height of your point. All right. So you assume that for some capital M, if you look at the points of height less than or equal to m, and if you start applying phi, well, you get many points which stay within the space of, within the set of points of height less than or equal to m. All right? Then the conclusion is that there is, you see, there is going to be a variety W psi defined over capital K, which projects onto B phi. So why is that? If you think of the points of height less than or equal to n, you can talk about them inside K. So you are going to get a certain variety in K to the whatever, m+1, something like this. And the endomorphism phi is going to induce some partially defined map on that thing. But the fact that you have many points that stay inside, that means that you're going to be able to find a sub-variety of this huge projective plane on which, and together with a map psi, which is going to be an endomorphism of that variety. Now, that variety might not be irreducible, so this psi is going to permute some of the components, but so you're going to get that actually, you are going to get a W psi, which is going to dominate some V phi to the R for some R. It turns out that actually this is good enough, and you can apply the theorem to deduce the conclusion. Now the assumption which I wrote there, saying that phi star of L is this vector bundle is stable, that phi star of L is isomorphic to Q tensor power of N. This is actually going to imply that the strong hypothesis of the result on the previous page is satisfied, and therefore you get the birational isomorphism. Okay. So I should mention this. This generalizes the result of Matt Baker. So he was the motivation behind our study. He proved the result for when V is equal to P1, and when the map is of degree greater than 1. Okay. So then, of course, since you are dealing with a complete curve, you get, your birational isomorphism is going to be birational. You can make it into an isomorphism. Okay. At least in characteristic zero. All right. So what I'm thinking of doing is to present you a bit of the model theory of the difference field which lies behind this result. And, well, I hope it will work out. So, please close your eyes again. Okay, so we're here. Right. So, the model theory of difference fields has been developed now for about more than 20 years, 25 years, I guess. It started with work of McIntyre, and then I guess after that myself and Udi Kruszowski and Petersil worked quite a lot on it. We have other names like Pilet, Scanlon, Belair, many names. Okay. So, as usual, when model theorists study a class of structure, they are interested in some universal model, and they look at the theory of existentially closed models. In other words, the models in which every system of difference equations, which has a solution in that extension, has a solution. Now, clearly, this cannot be quite possible the way I stated, so you need to impose a bound on the size of the system of equation, right? Okay. So these fields, they are known to exist just by general nonsense. They are very useful. They play the role that C would play for algebraically closed field of characteristic zero. Namely, it's a big field in which anything that can happen happens. As with algebraically closed field, there are natural invariants attached to those difference fields. For instance, just the characteristic, but also what sigma does to the algebraic closure of the prime field. It turns out that these things are enough. And while the theory does not eliminate quantifier, basically this is only if you know the isomorphism type of an algebraically closed difference field, then you know exactly what the definable sets are. All right. We know exactly its type. So the theory has some model theoretic property, as I saw. So, as I said, if you are within this monster model U, you look at an algebraically closed difference field, then its isomorphism type will determine which formulas with parameters in that difference field are satisfied in the big model. Okay. Right. So the theory is what's called super simple. It has large rank. In other words, if you take an element whose transforms under sigma, an element A such that A, sigma of A, sigma square of A, and so on, are all algebraically independent over the ground field, then you're going to get something which is complicated, which has a complicated. It eliminates imaginaries, meaning that if you have a definable equivalence relation, then you get zero definable equivalence relation, then you get a definable map from the classes to some set which lives in the real world. So that's quite useful to do certain things. And one of the main results in the area, which is at the source of most of the application, is the fact that, so you want to study sets which are sort of small. In other words, sets in which so sets defined by difference equations, or maybe some existential formulas, but in which every tuple of solution will satisfy non-trivial difference equations. In other words, if you take a solution, and if you take the difference field generated by that solution over the ground field of parameters, this should have finite transcendence. So these types are nice. They have what we call finite rank, a rank which is associated to the independence. And having finite rank means that you can sort of describe them in terms of things of rank 1. So if you want to understand the structure of definable sets, it's important that you understand the structure of sets of rank 1. And the main result is this thing, which was proved first in characteristic 0, and then in characteristic P, with a quite different proof, and which is to say that either, if you take solution set of a type of rank 1, it's either 1-based, I'll give the definition at some point later, or it's going to be internal to the fixed field, as I said before, at the cost. So you have your element, your tuple A. It turns out, over your set of parameters K, it turns out that if it's non-orthogonal to the fixed field, to fixed sigma, then actually the difference field it generates, that A generates over K, is going to be of transcendence degree 1. And what happens is that maybe at the cost of increasing K, you are going to get that A is equi-algebraic with some B which satisfies sigma of x equals x, all right? And you have a similar state. In characteristic P, you have, of course, you have the other fields lying around, which are the fields defined by these equations obtained composing sigma with powers of the Frobenius, or sigma to the n with powers of the Frobenius. Okay? In characteristic P, you get many fields around. All right. Okay, let me continue. So this theorem is really what is at the source of application. So usually what happens is that you try to, so the usual applications where you have a set, let's say for instance the set of torsion points in an abelian variety, and you want to intersect it with a variety and see what you get, right? And typical result you want is that the Zariski closure of the set is going to be a finite union of cosets of subvarieties. So the typical strategy that model theorists have used to do that is to put this set of torsion points inside something which is 1-based. Because it turns out that if you are 1-based and if there is a group law around, then you have a property which is called weak normality, and which says that every definable set is a Boolean combination of cosets of subgroups, of definable subgroups. So that gives you immediately the intended result. So these are the type of applications which were done in the past. In our case, I mean, we don't have any group lying around. And it's actually, the application comes from really pure model theory, and I found it very surprising. Okay. So it comes from this property which is called the canonical base property. So, canonical base, so you have a set which is definable, okay? So it's going to be defined, let's say it's defined by just difference equations, all right? So there is, because we eliminate imaginary, there is a smallest difference field over which it's going to be defined, okay? So this smallest difference field is going to be what we call the canonical base of our definable set, all right? Now, this difference field is going to be finitely generated as a difference field, all right? So you can now change the viewpoints, which means I was looking at a generic of my difference variety. Let's call it A. No, let's call it B. So I take the generic of my variety B, and now I look at the generator for my field of definition. All right. So let's call it A. Now, instead of looking at B over A, which I did by looking at the variety which was A definable, I'm going to look at A over B. It also satisfies some kind of equation. And now I'm sort of shifting the emphasis. And the thing is that this canonical base property is going to tell you that, well, A over B is not just anything, it's going to satisfy some very strong conditions. All right? So, this property was first isolated for complex analytic spaces by Campana and Fujiki. So they determined that in that case, this thing had to be Moisheson, what we call Moisheson. It was sort of rediscovered by model theorists at the beginning of the 2000s, and I guess the names of Pillay, Moussa, and Ziegler are very important in that, because they saw how this property could be exploited, translated model theoretically. And in particular, Pillay and Ziegler, what they did is that they showed directly with a very easy, very elementary in the sense that it doesn't use anything, proof using jet spaces that differentially closed field of characteristic 0 had this property. So if you take a differential variety of finite order, then you get things like that. And they also showed that the difference field of characteristics 0 had the property. However, they didn't show that it worked for characteristic P. Right. So, okay, in order to explain how this works, let me first give you some result. So, as I said, sets of finite rank can be analyzed in terms of rank 1. So how does it exactly work? So let me take a difference field K, a tuple B, such that the difference field generated by B over K has finite transcendence degree over K. Then you're going to produce a sort of analysis of this extension and decompose it as a tower of sub-extension where each sub-extension is of a given type. All right? So actually, in the real world, it doesn't happen quite like that. I mean, in order to get this fine result, having, the AIs, really working with sub-extensions, well, you have to work a little, but, okay, it can be done. And the thing is that the sub-extensions are going to be a special type, so either they are going to be algebraic, that's not very interesting, but, or else they are going to be internal to a fixed field, again, this famous fixed field. So that means that if you look at the difference variety defined over K over AI sigma, of which AI plus 1 is a generic, then this sort of embeds into the fixed sigma rational points of the variety. Okay? Or the third possibility is that this is one-based. One-based is this wonderful property that makes things work. We are going to see a bit more about it later when I give the definition. So here's the definition. So let's say we have an A-definable set. It's going to be one-based whenever you take an n tuple in that set S, so A1, AN in that set S, and you take some extension of the base set A, then the elements of the tuple A and this B are independent over the algebraic closure of AA and B. Intersection of the algebraic closure of AA and B. So what does it say? It says the following. You look at A, which is a generic of your difference variety, which is defined over capital A, right? Now you increase the base field capital A to a large algebraically closed difference field B. Maybe A is not independent. I mean, maybe A is going to satisfy some additional difference equation, right? One base says that the coefficients of these difference equations, they are in the algebraic closure of the field, of the difference field generated by little a over capital A. So this is a very strong condition. So for instance, you notice that fields don't have it, right? Because let's say you are over Q, you take ABC algebraically independent, and then you take D equals AC plus B. Well, that you have that the algebraic closure of AB and the algebraic closure of CD, they intersect in the algebraic closure of Q, but certainly they are not independent, right? Because they satisfy, I mean, AB are algebraically independent over Q, CD are algebraically independent over Q, but AB are not algebraically independent over Q, CD. Right. Okay. The second, internality. So internality, again, so this, we have some set which is definable over A, we have another set which is definable also over A, let's say, and you say that the first one, that S is internal to P, that means that at the cost of maybe increasing the base, you are in the definable closure of things of solution of P. S. And these things occur, I mean, for instance, to be fixed of sigma internal, people who work with difference fields have seen them all the time. I mean, if you take your favorite difference equation, linear difference equation, sigma of x equals ax, you know that when you add a fundamental solution, then all the others are obtained by implying, by multiplying by element of GLM of the graph of the base field. So this is a typical example. Right. Okay. What am I doing? 5 minutes, right? 8. So this was an example of an analysis of, I mean, basically the way I'm stating this example, it's already there. The analysis is there, but actually you have several ways of doing it, of course. And I should say that one can show, at least in characteristic 0, that the extensions of coming from 1, 3, and 4, they are one-based. But of course, the extension sigma of A2 minus A2 equals A1. This is internal to fixed sigma, because once you have a solution, all the others are obtained by adding an element fixed by sigma. Right, so the canonical base property says that assume that, so we have this B, which satisfy a difference equations with coefficient in the difference field generated by A. And we assume that really we need all of A for that. In other words, that if you take the algebraic closure of the field of definition of that difference variety, then you get A's inside. And the conclusion is that, so that's what I mean by, in other words, A is a canonical parameter for the difference locus of B over A. And the canonical base property tells you that the type of A over B in other words, if you look at the difference variety that, if you look at it now in terms of A over B, that this should be almost internal to fixed sigma. In other words, at the cost, if you look at that difference variety, it's going to be isomorphic to the fixed sigma ration, let's say in characteristic 0, to the fixed sigma rational point of some algebraic variety. One can actually show slightly more. I mean, one can show that not only the type of A over B, but if you look at the intersections of the algebraic closure of A and B, then you get that this type is internal too. Okay. Right. How does one prove it? Well, one does some kind of decomposition theorem. In other words, you are going to look at your A over B, but you are going to split it into what I would think primary components. Okay? So in other words, all the elements in the analysis, I mean, if you take one of the AI, all the elements in its analysis are going to be internal to the same type PR. Okay. Right. So as I said, the canonical base property was shown for difference field of existentially closed difference field of characteristic 0. So in characteristic P, the methods do not apply. However, so how would one go to do it? So first of all, you use the preceding result to reduce to the case where the type is analyzable in fixed tau, for some tau which is sigma to the n, for venus to the n. Once you have done that, you can sort of reduce to the Pillet proof, to the Pillet-Ziegler proof, and you get the results. So that's how you prove it. Okay, and what we are using is the following. That's what gives the descent, really. And it says here, so I stated it first in the very model theoretic manner. The funny symbol there just says that A1 is independent from B1 over B2. So in other words, here I have some fields, B1 and B2, fields of definition of difference variety. I'm taking A1 and A2, they are going to be generics of this difference variety, but generics over B1, B2. In other words, if you look at A1, it does not satisfy more equations over B2 than it did over B1. Over B1, B2 than it did over B1, and same thing for A2. And you're assuming that A2 is actually algebraic over B1, B2, A1. So this corresponds, if you remember what I was trying to prove. So my A1 will be the generic of my variety W psi, of my algebraic dynamics W psi. And the A2 is going to be the image under G, under G of this generic. Okay? So this is really the setting. And the conclusion is that under that situation, you have a D which is contained on the right-hand side part, the B2A2 part, and which... wait, is that what I wrote? No, I wrote something stupid there, I'm sorry. Such that, so ignore that sentence, such that the type of A2 over CD is almost internal to S. And D is independent from B2. All right? So this is the result that we are going to use. This is exactly what we have to use. All right. So I found, yeah, this is a purely model theoretic result, which is proved using forking and all kinds of things, and it's surprising that it would have applications to algebraic dynamics. Okay, thank you. Thank you, Zoe.
Thank you.
Questions?
more complicated than characteristic P, but you get the same result?
Yes. No, I mean you get a canonical base property, but via this trick of changing, of considering just one automorphism.
Actually, have you thought about this canonical base in terms of p-stable formulas that is known for any supersimple series?
No,
so
actually,
the names of
there are examples of series which don't have it. I mean,
no, that's generally true.
What?
That's generally known for any supersimple series.
What?
The canonical base in terms of collection of names of p-stable formulas. Okay.
I'm sorry, I don't understand.
I'll talk to you later.
So yes, I should say that, okay, this canonical base property, not all theories have it. And Hrushevsky and like canonical base property, no. There is an example by Hrushevsky and some other people where you have something which is definable inside algebraically closed fields, actually, and it doesn't have the canonical base property. Well, I'm sorry, Björn.
You mean existence of the canonical base?
The canonical base property, I mean the fact that the type of the canonical base over realization has this very strong property of internality, this just is not always true. And there is a fairly simple example of where it fails. Now, okay, it was an example that was devised to make it fail. I mean, it's hoped that in most structures that we're looking at, that it doesn't fail.
The dichotomy theory is also for any supersimple with finite assuming. I mean, dichotomy. Is there any dichotomy theory for any supersimple having a finite?
No. I guess I should say that this conjecture, I mean, this dichotomy, this is motivated by a conjecture of Zilber, which was refuted by Hrushevsky, which is to say that when you have things of rank 1, there is a notion of geometry or pre-geometry given by algebraic closure. And the conjecture was that either this geometry is locally modular, or else it's because there is a field lying around. Okay? So the conjecture was disproved in the case of... But sort of, let's say that in the natural algebraic examples, it stays true. And this is what makes things work. And what happens is that this one-based definable set, so either the geometry is totally is disintegrating, meaning that the algebraic closure of the set is just the union of the algebraic closures of elements, or else you have a group law, in which case the structure that you get on this is no more complicated than the module. Okay? But as I said, there are examples where the conjecture, this dichotomy fails. I mean, that you have things which are more complicated than modules, but not as complicated as fields, or more complicated than fields. Okay.
Jim?
Is there any currently studied or natural class of examples of theories where it makes sense to attempt to actually prove CVP?
Well, okay, so first of all, it only works for things of finite rank.
Yeah.
Okay? The one outstanding question is what happens in separably closed fields of finite degree of imperfection. There, you are going to have to study things which are analyzables in terms of the perfect core. In other words, perfect core is just the intersection of all k to the p to the n, right? this is the only non-modular type, non-one base type of rank 1. So by the result that I showed, this sort of decomposition result, you have to look at types which are analyzable in this thing. So there is a partial result by Pillay and Ziegler where they introduce this notion of very thin types. They show that if you look at very thin types, then the canonical base property works. Unfortunately, types which are analyzable in this intersection of k to p to the n are not necessarily very thin. And there are examples of things which are analyzable in 2 steps which are not very thin. So that's the next thing to prove, but you know, separately closed fields are horribly complicated. I mean, they're just awful.
So CBP is open.
CBP is open for that. I mean, it's hoped that they should satisfy it, right? But you see, the problem is that the proofs of Pillay and Ziegler, they use jet spaces. So automatically, as soon as you have if you have inseparability around, an inseparable map around, then things get killed, you see? So that's...
Okay, let's thank Zoe again.